In this video, I want to do a quick review of section 2.1 through 2.3, stuff that you would see in the textbook when you read it, but I just wanted to go through a quick example in the back of the book. So here's that question. It's number 16 through 19 on page 95, and it talks about the expenditures of colleges and universities over the past 4 decades. So in this table, we have some information and we have some missing information. So let me highlight the given information over the decades. So every 10 years, they collect the expenditures of the colleges and universities and compile them. And so I wanted to make a note about this, a little exclamation mark, that these numbers are in millions. So in fact, this number right here, what looks to be 21,043, is actually 21043, and then 3 zeros are missing, that million. So this is actually 21 billion, quick edit, 21 billion $43 million in 1970 rather. So the first thing we want to do is, what trend does this table exhibit about expenditures? And so clearly, if you look at the highlighted numbers for the expenditures, these are increasing year over year. And then the next thing we want to do is estimate the expenditures for 1975. So that's that first missing box. There's several ways that you could do this. One quick way is to notice that 1975 is halfway in between the 70s. So 1970, 1980, 1975 is halfway in between. So one way you could calculate this number is to do 56,914 plus 21,043 and divide that by 2. And you would get 38,978.5. And so we can fill that number into our table. 38,978.5. Okay. And then the second way we could do this, get rid of this quick calculation, is by the formal way that the textbook introduces. And that's to first find the slope, which would be the change in the dependent divided by the change in the independent. So in this case, the expenditures are dependent upon the years. And so we want to find the change in the expenditures over that decade from 1970 to 1980, and then divide that by the change in years. So we would do 56,914 minus 21,043 divided by that 10-year difference, and that gives us 3,587.1. So that was the change for 1 year. So this would be millions of dollars per year. And since it's per year, that's a single year's growth in that decade. So what we'd have to do is take that number and add it to the year 1970. So I would take the year 1970, which we had an expenditure of 21 billion 43 million, but we're not going to write all those zeros, plus this number, and then I have to multiply it. Let me erase that little smudge. Multiply it by 5. Okay, so multiply the slope by 5 because it's 5 years from 1970. And so if we do that, we get the exact same number that we got originally. So why would we have two different ways? Well, that's the problem in number 3. And so for 1975 is a special number because it lies halfway in between 1970 and 1980. But what happens when we don't have a number that's exactly halfway in there? So let's look at that when we try and find 1991. So now, over here in 1991, we're looking at this decade, and 91 sits just 1 year above 1990. So now I can find the slope in the 90s, and so that would be 236,784 minus 134,656 divided by that 10-year span. So if I do that calculation, I get a slope of 10,212.8. Again, this is millions of dollars per year. And so to find the value in 1991, we would take that slope and add it to what we had in 1990. So 134,656 plus 10,212.8. And technically it's multiplied by 1 because it's 1 year above 1990. So if I go ahead and quickly type in that calculation, 134,656 plus 10,212.8, I get 100, I get 144, technically that's billion, 868 million, and then 0.8, which would make it 800,000. But nonetheless, we got the number that we wanted, which should be the same calculation here. I just filled it in the table. Alright, so we got those two numbers. Let me clear some of this clutter off of here. Alright, so we filled it into the table, but these two numbers, 1975 and 1991, are particularly special. So since we're trying to predict a value that's inside of the data range that we're given, this type of prediction is given a name, and it is called interpolation. And the way I remember that this is interpolation is that it is inside the given data set. So in contrast, here in number 4, we're going to look for 2018, but 2018 is outside, so this is called an extrapolation. It is a prediction outside of the given data set. So how are we going to find 2018? Well, this time we're going to use the closest decade to 2018, which is the 2000s to 2010. And then once again, to extrapolate, we're going to find the slope. So we would do 461, 100,000, and then 236,784 divided by 10. And here we get a slope of 22,421.6, or actually 22,421,600,000 if I'm being technical, but so that's how much it's changing. And then what we're going to do is take that number in 2010, when we had $461 billion in expenditure, and I'm going to add 22,421,600,000 written like that. And so there are 8 years from 2010 to 2018, so I need to multiply that change by 8. And so if I quickly do that calculation, let's see, 22,421.6 times 8, and then plus the original 461, then you get quite a bit, 640,372.8 millions of dollars in 2018. So since this is really $640 billion, we're looking at over $500 billion of expenditures is predicted in the year 2018. Of course, we really won't know until they collect more data in the year 2020, but using this mathematics, we can try to predict. Now, the next thing I wanted to talk about was something that's really discussed in 2.2 and 2.3, which is the types of graphs. So in Excel, I quickly created this graph and just wanted to point out some features here because I've tried to make it to where it's not the best graph that we should use. One reason is on the vertical axis, I have started at 50,000. That's not very good. What we really want to do is start at 0. So starting at 0 is the best because it doesn't shrink our data. Also, you might notice that there is a pretty large gap from the highest number up to the largest indicator there, which again makes this look like it's not too much of a steady slope. So if you look at this, you're like, oh, it's not really growing that much. It's average. Maybe this is average inflation. But let me change it to where I'm not trying to mislead you. And so notice now here on the vertical axis, I've started at 0 and my highest goes up to 500,000, which are numbers that were relatively close within my table. And you can see that over certain spots, we have, so for example, over this area right here, like we have a drastic increase, as where our other graph didn't really illustrate such a drastic increase. And so this is our line graph. We've connected the points. So technically I have a data point here, 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 and there. And there's where the values. I've excluded the 1991 because that was a prediction. And I've also excluded, that should be 1970. And I've excluded the 1975 one also because, again, it would probably lie right there, but that was a prediction, not an exact. Alright, so that wraps up my little review of sections 2.1 through 2.3, and I hope you find that helpful.